Hey everyone. Well, after learning about our general or universal force of gravitation, we're going to go back and look at our gravitational potential energy. We're going to see the more broad equation that we can use to apply for anything, whether it's in our solar system or anywhere else in space, and some weird little attributes that this equation is going to have. So, to start out, let's go back to our basic gravitational potential energy. Here was our equation. The gravitational potential energy of an object is based on the mass of that object times g times h, where h is the height. And we used to normally say, like, all right, we'll take right here as being h equals 0. And that was fine. We said, okay, we're holding up this apple or whatever it is. This has a certain height. And we can figure out relative to this ground level what UG is, or looking at the change in UG based on the change in height if the ball was to fall downward. And we would plug in some positive height because it's some positive value from here to here. Well, some students think, and some even ask me, what if we didn't pick H being 0 right there? What if we picked it at a spot like the ceiling? We've mentioned how that spot really is arbitrary because, again, what we're measuring is the change, the ball going from one spot to another spot. Let's see if we picked right here as our h equals 0. Well, there's no problem with that. Right now, the ball is located some negative height, some negative amount. Well, if I did this, when I write my equation, UG equals mg, it's a negative h relative to the ceiling. Again, I'm comparing 2 points. Here compared to here, it's a minus h. But to be honest, that's okay. Yeah, I get a negative gravitational potential energy, but that doesn't really matter as long as I'm consistent. Okay, as long as this is always my starting point, my 0 point, I can still approach any conservation of energy or gravitational potential energy problem. It even still works if you imagine the object falling, right? As it's falling, this negative h is getting bigger and bigger. If negative h is getting bigger and bigger, this here becomes a smaller, a more and more negative. If something's getting more and more negative, that means it's getting smaller and smaller. And that matches, right? When things fall, as they're falling down, their gravitational potential is going down, getting smaller, as, say, their kinetic energy is going up. So if I picked my measuring spot from above or further away, beyond where that object's going to move to, you just get a negative. But to be honest, it doesn't really change anything, okay, as long as you're being consistent. This is a key idea going forward. Okay, well, we saw in a prior video the equation for the universal force of gravity. So we're not just going to use the weight now. So let's go back and re-derive our equation for gravitational potential energy. Okay? We figured out gravitational potential energy by looking at the work that's being done. Well, the work that's being done is based on the parallel force times the displacement. Again, if I have, I don't know, maybe this is a satellite that's orbiting a planet, okay? If I'm looking at the work, that's the gravitational force times r, where r, again, is the distance between the, that was a terrible line, between the centers. So Fg, here we go, gmm over r squared multiplied by the distance, or the displacement, that's r. Well, I'm going to cancel out one of these r's right here. That's going to cancel with that. And I'm left with g times m divided by r. That's the work that's done by gravity, and this is what we called gravitational potential energy. This is our general, our universal equation for gravitational potential energy. So grav potential energy. And again, it's important to point out that we measure UG from some reference spot. R is some spot we need to choose. And to be honest, this is where this equation gets a little weird. Where are we going to measure from? When I went back to this slide, we just measured from like ground level because that makes sense to us on Earth. If I'm looking now universally, it would be weird to pick like the surface of the Earth to measure R from. That'd be a strange thing because depending on where these things are, you might have different values, or you'd always have to measure from planet Earth, and planet Earth is moving. It's a weird thing to do. Earth isn't special in any way. So we're not going to measure from planet Earth. Well, are we going to measure from like one of these specific spots? Again, that's maybe a little unclear. Physicists like to follow a convention. Just like we followed a convention pretty much of always choosing ground level for H, there's going to be a convention for where we're going to measure R from. Let me get rid of this slide here. Well, we are going to pick a spot. We are going to measure R from a location that is infinitely far away. And that seems really weird. We're not going to pick R from right here, because that's going to vary depending on the object, depending on the distance between any two objects. It's not going to be constant. Okay, we're going to say that R is infinitely far away. For all things, if you're infinitely far away from everything. And if that's the case, well, gravitational potential energy is very similar to this example. When I picked my origin, my H equals to 0 is above. If my R is going to be 0 from infinitely far away, then I have 0 gravitational potential. Look at this equation. Okay? If R is infinity, gravitational potential is nothing. And that probably makes sense. If something's infinitely far, nothing's going to fall on top of you. That's not really possible. So we measure R from a spot infinitely far away. And if something is being measured from infinitely far away and things are being brought closer together, it's just like when I was measuring H from up above. I have here an infinitely far spot, so the distance is going to be a negative amount. The equation that you're always going to see for gravitational potential has a negative right here. And it's precisely because of this. Okay? To be honest, if that's a weird thing to think of, and it is, picking R infinitely far off, it doesn't really change anything. Just like it didn't change anything in this example, we can still look at the change in height. We still know that as the apple falls, gravitational potential energy gets smaller. All of that is still true. Okay? As this mass, if it was to get closer and closer and closer, R is going to become, well, a negative number that's getting more and more negative because I'm dividing by a smaller thing. This number here is going down and down and down, smaller and smaller. So UG is going to become more and more negative. Just like before, if something's getting more and more negative, it's getting smaller. And all we really care about is the change, going from one spot to another spot. So the reason this is a minus is because we're measuring these R's from a spot infinitely far off. That's our reference frame. Okay? You'll still plug in the distance between the objects, but because that reference frame is from a spot infinitely far away, you get this negative. Just like, again, up here, we could still plug in the height something is falling, but relative to a spot high up, you get a negative value. That's weird, but it doesn't change anything. We still have gravitational potential. It still makes sense when we're talking about things getting closer as they convert from one type of energy into kinetic, say, the gravitational potential should be getting smaller. And it does, following this formula with that negative. Because there's a negative, the graph might look a little weird, and you could see this graph on the AP test. Gravitational potential is negative. And I have this relationship between UG, oops, let me get my pen, between UG and R. It's 1 over minus R squared. So this is the function. All right, that potential energy approaches 0 when I get more and more R, when R gets greater and greater. And just it's negative here, so when things are closer together, they have a larger negative value. So you might see a graph like this, but again, don't really freak out about it. it's still our same conservation of energy. This is the last thing we're going over. We know by conservation of energy, the initial energy should equal the final energy. That's the basics. Well, normally we would do Ke plus Ug, and since it's always equaling the same amount, it would equal some constant. But now, slight change. The process is still the same, but it's Ke plus this negative Ug. That equals a constant. Or, rewrite it one last time, Ke minus Ug equals a constant. So that negative is in there based on this conventional reference frame, okay? But you can still apply conservation of energy. We still know when Ug gets smaller, another form of energy should be getting larger. All right? We still know that when things get closer together, the gravitational potential energy should be getting smaller. None of that's changing. The last thing right here, then I'm all set. When we're looking at the energies of objects, recall that a single object has kinetic. We have to include multiple objects. We have to look at systems when discussing gravitational potential energies. Okay, we'll get practice with this coming up shortly. Thanks for watching.